Hello, sir. My name is Group20. My student ID is 2002980. And now I'm going to present about background of smart parking. Parking shortage and traffic congestion has spread throughout our increasing urbanized world, lowering the quality of life in cities. The inadequacy of traditional parking management techniques to address this issue has prompted the development of new approach. Among these options, smart parking has emerged as a technologically promising approach to increasing parking availability and improve urban mobility. It removes the development of various sensors, cameras, and software solutions to monitor and optimize the utilization of parking space in urban or crowded areas. The origin of smart parking can be traced back to the later half of the 20th century, when urbanization and increased automobile ownership put a strain on parking infrastructure. Automating parking space and implementing electronic payments methods were early attempts to address parking issues. However, the early 2000s saw the development of sensor technologies, which laid the groundwork for today's smart parking system. The development of magnetic, ultrasonic, and infrared sensor ushered in the new era in parking management by enabling the detection of vehicles in parking space. Smart parking system aims to alleviate common parking issues such as finding available space, reducing traffic congestions, and improving overall urban mobility. Next, once on the Internet of Things, which is IoT, and data analytic technologies have pro smart parking system to a new level of sophistication. Real-time data collections and analysis enable more efficient use of parking resource, allowing drivers to find available spaces faster and reducing unnecessary circling. The integration of mobile application further transformed the user experience, allowing drivers to research parking spot ahead of time, make payments seamlessly, and receive real-time updates on parking availability. Furthermore, smart parking integration with other urban systems, such as traffic management and public transportation, allow for a more comprehensive solution to urban mobility challenge. Next, pilot programs for smart parking have emerged in cities around the world, serving as innovations testbed and demonstrating the viability and efficiency of various technology. This initiative enabled the large-scale implementation of smart parking infrastructure. Investing in sensor, cameras, and digital signage throughout parking lots enabled governments and municipalities to transform traditional parking lots into intelligent, data-driven spaces. Now, smart parking has significantly impacted urban mobility. Smart parking not only reduce traffic congestion and emissions, but they also improve overall transportation efficiency by reducing the amount of time spent looking for a parking spot. Furthermore, because smart parking provides the drivers with greater convenience and predictability in their parking experience, it improves their user experience and specifications. Furthermore, smart parking system promotes sustainability by reducing the needs of additional parking infrastructure and encouraging alternative modes of transportation through optimizing parking utilization. Next will be problem statement. Inefficient parking structure are a major cause of heavy traffic, pollution, and annoyance for drivers in cities. Drivers frequently circle around in search of available spots when parking spaces are scarce or poorly managed, which increase traffic congestion and gridlock. This increases air pollution and greenhouse gas emission in addition to wasting fuel and time. Furthermore, driver mental health and driving experience may suffer because of stress and frustration brought out by lacking of parking. Therefore, tackling parking inefficiency and congestion is essential to lowering traffic and enhancing urban mobility. Moreover, one of the primary elements that leads to parking congestion is the restricted supply of parking spots. Many parking policies in the place today don't effectively maximize the use of spaces that are already there. Static pricing model or time-based restriction are common components of traditional parking management strategies, which fail to account for variations in demand throughout the day. As a result, some parking lots may be severely congested during peak hours and underutilized during off-peak hours. The effectiveness of parking emission initiative is a general weakened, and parking problems are made worse by this inefficient use of parking resource. Furthermore, the issue brought on by parking shortage and congestions are made worse by manual and ineffective parking operations. Many parking facilities still primarily rely on manual procedure for ticketing, payment, and enforcement. This leads to operation delays, inefficiency, and human error. Driver may become confused and irritated with manual parking operations, since they are prone to mistakes like overbooking, double booking, and inaccurate fee calculations. Next, objective. Our objective is to develop a system that utilizes the existing cloud providers that can assist drivers when they're finding parking to decrease the chance of parking congestion and enhance the effectiveness of parking spot. In this project, we will utilize Amazon Web Services, which is AWS, as the main platform for our parking system.
For the study of different cloud platforms, I have reviewed 3 different cloud computing platforms. First is Amazon Web Services, also known as AWS. Second is Microsoft Azure. Third is Google Cloud Platform, which is also known as GCP. For the first one, Amazon Web Services, also AWS, it begins with the launch of Amazon Simple Storage Service S3 in 2006. It is one of the leading providers of on-demand cloud computing resources and also offers over 200 fully featured services. It operates a global infrastructure with over 100 availability zones and also provides high scalability and elasticity for users. Its key features are Amazon EC2, which used to launch virtual servers with specific configurations. AWS Lambda, which used to execute codes in various languages in response to events. Amazon S3, which is used to store and retrieve data of any amount. Amazon DynamoDB, which is a fully managed NoSQL database suitable for applications requiring low latency. AWS IAM, which is used to control access to AWS resources, managing users, groups, roles, and permissions. And lastly, AWS IoT Core, which is used to facilitate secure and scalable communication between IoT devices and cloud applications. For the second cloud platform, it is Microsoft Azure. It is announced in 2008 as Windows Azure and officially launched in 2010. It has grown rapidly throughout different eras and became a cornerstone of the cloud computing industry today. It also seamlessly integrates with existing Microsoft products such as Windows Server, Active Directory, Office 365, and Visual Studio. It ensures a familiar and consistent experience for all users with existing skills and investments in the Microsoft technologies. For its key features, the first is Azure Virtual Machines, which is used to deploy and manage virtualized Windows and Linux servers. Azure Functions, which is used to run code in different languages in response to trigger events. Azure Blob Storage, which is a scalable object storage service for unstructured data by organizing them into containers and blobs. Azure Cosmos DB, which is a globally distributed multi-model database service supporting multiple data models. Azure AD is a centralized identity repository that provides single sign-on capabilities and multi-factor authentication. And lastly, Azure IoT Hub, which enables bi-directional communication between IoT devices and Azure cloud applications. For the last cloud computing platform, it is Google Cloud Platform. It is launched in 2008 with Google App Engine and remains at the forefront of cloud computing through continuous innovation and expansion. Its infrastructure is built on the same global network that powers the Google's renowned services like Search, Gmail, and YouTube. It also offers BigQuery for lightning-fast data analysis and Google Cloud AI platform for customizable AI solutions. The GCP's embrace of open source technology also fosters collaboration and interoperability. Its key features are Google Compute Engine, which is used to deploy and manage virtual machines in Google's data center. Google Cloud Functions, which is a serverless compute service allowing developers to run event-driven functions in response to cloud events. Google Cloud Storage, which is a simple, cost-effective storage solution for any type of data and organized into containers called buckets to store data objects. Google Cloud Bigtable, it is a fully managed, scalable NoSQL database service designed for massive workloads of structured data. Google Cloud Identity and Access Management, it is used to manage the access control and permissions for resources within a Google Cloud environment. And lastly, Google Cloud IoT Core, which provides a secure and reliable way to connect IoT devices to the cloud applications. Now for the comparison of the relevant cloud platforms. For computing services, AWS will be using Amazon EC2 and AWS Lambda. For Azure, it will be using Azure Virtual Machines and Azure Functions. For GCP, it will be using Google Compute Engine and Google Cloud Functions. Next, for storage services, AWS will be using Amazon S3. For Azure, it will be using Azure Blob Storage. For GCP, it will be using Google Cloud Storage. And next, for database service, AWS is using Amazon DynamoDB. Azure is using Azure Cosmos DB. GCP is using Google Cloud Bigtable. And as for the security service, AWS is using AWS IAM. Azure is using Azure AD. For GCP is using Google Cloud Identity. And for the next service is IoT service. AWS is using AWS IoT Core. Azure is using Azure IoT Hub. And for GCP is using Google Cloud IoT. As for their unique strengths, AWS has the largest market share and has the most extensive range of services. Its constant innovation and customer-centric, it also has a constant innovation and customer-centric approach. Azure IoT Hub, it integrates seamlessly with existing Microsoft products and seamlessly extend organizations on-premises infrastructure to the cloud. As for GCP, its expertise in data analytics, machine learning, and developer-friendly services, and offers a unique set of capabilities tailored to modern application development and data-driven insights.
Hi, my name is Evasion and I'm going to present the architecture diagram of this project. First of all, on the side of the web applications, users can utilize the application by accessing the website hosted in AWS Amplify via their phones. Users can then sign up an account if they are first-time user and log in using their existing accounts. The user authentication and authorization are done by AWS Connector, where it will add newly signed up user account into the user pool and redirect authenticated user to the homepage of the application. Next, the application will then retrieve relevant data from AWS DynamoDB, such as the status of the parking space, which indicate whether there is a vehicle parked there, safe payment method for automatic payment, and many more. The application is capable of displaying the real-time data of parking slots by subscribing to AWS DynamoDB. If there is any update in the database will return updated data to the application, where the application will display the real-time data, the parking space status is specific to the users. Moreover, users are able to select and reserve parking space in spaces they desire. After submitting the reservation request, the application will trigger an AWS Lambda function which will update the status of the parking space to park and subsequently trigger another AWS Lambda function that will change the signal light color of light indicator installed in every parking space to indicate the status of the particular parking space. Additionally, the AWS Lambda function will also trigger another Lambda function to create scheduler that creates schedule in AWS EventBridge scheduler to track the expiry time of the reservation. By default, the expiry time will be 1 hour from the time user had reserved the parking space. If the schedule reached the expiry time, it would invoke AWS Lambda function to update the status of the parking space back to unparked and update the signal light color. When users park their car in the reserved parking space and leave after some time, the system will start to calculate the total cost and return the value to users for payment in the application. Users may choose multiple payment methods and save the selected payment method for automatic payment next time. For this purpose, the application will get the saved payment method stored in database and check if there is any saved payment method. If there is a saved payment method, the system will help users to make the payment using the saved payment method automatically. On the side of the IoT, there are weight sensors and cameras installed in every parking space to detect whether there is any vehicle parked there. They are connected to AWS IoT Core using private keys and certificates and subscribe to topics that are used in differentiating the parking space. If weight sensor detected changes in weight, the camera will then start to capture the car plate of the vehicle and publish the data to the topic subscribed in AWS IoT Core. Then it will trigger a AWS Lambda function to check the slot status of the parking space and update the database and signal light color accordingly.
In conclusion, we explore how smart parking has evolved from being a simple congestion solution to becoming a sensor-driven management system. Our objective has been clear, which is to provide a real-time data, streamline reservation and payment, and enhance accessibility for users. In terms of deployment, we have discussed the utilization of sensors, cameras, and cloud-based applications, which offer convenience and contribute to congestion reduction in urban areas. Moving to our smart cloud platform review, we compare AWS, Azure, and GCP. AWS stands out for its comprehensive services and global infrastructure, while Microsoft Azure offers seamless integration with Microsoft products and hybrid solutions. GCP excels in data analytics and has a strong focus on machine learning capabilities. We then delve into the proposed architecture, leveraging AWS services such as Amplify, Cognito, DynamoDB, Event-Bridge Scheduler, IoT Core, and Lambda. This architecture facilitates user interaction, authentication, real-time data storage, reservation management, vehicle detection, and status updates. Looking toward the future, we have discussed various avenues for improvement, including scalability, enhancement to accommodate larger facilities and user demand, integrating machine learning algorithms, which can help in predict the parking demand and optimize resource allocation. Additionally, advanced features like dynamic pricing, real-time guidance, and integration with smart city infrastructure to hold promise for further enhancing the system. Exploring emerging technologies such as blockchain, edge computing, and 5G connectivity can unlock new opportunities for the innovation. In conclusion, the integration of smart parking system with cloud platforms represent a transformative step towards creating smarter and more efficient urban environments. Thank you.
So now we will show how we configure the AWS services that we are using in this project. First of all, you need to have a AWS free tier account and you have to sign into the console. And this is the AWS console after you have signed into it. And now we will start by configuring the AWS IoT Core. So on the search bar, search for IoT Core, and the console will then redirect to AWS IoT Core console page. Then on the side navigation bar, expand all devices and select things type. You need to create a thing type by entering the thing type name. And in this example, the thing type name will be weight sensor. And this is the thing type that are created after completing the last step. Now, on the side navigation bar, select one device, and it will show you this page which will tell you to prepare your device. And now click next in this step 1. In step 2, create a thing by entering the thing name and selecting the thing type they are created previously. In step 3, select the platform and AWS IoT device SDK, which in this case will be Windows and Python. Now we will see this page in step 4. Note that the policy is auto-generated for the thing. Now download the connection kit and unzip it into a folder. After unzipping the file, now open PowerShell and change directory to the folder containing the unzip files and copy the command shown in step 4 and run them. For demo purposes, the device will be our computer and we can see that the device are able to connect to IoT core and successfully publish and receive return message. We can see the same results in step 4 in the console. After confirming the device is connected, click continue. Now, finally, we can see that the thing is successfully connected and connected to IoT core. After successfully created the things, now expand all devices on the side navigation bar and click links. And we can see that the thing is successfully added to the list. Now I will show you how we created the AWS Lambda function on the AWS console. On the search bar, search for Lambda, and the console will then redirect to AWS Lambda console page. And now click Create Function button, display on the top right corner. Now enter function name, select runtime and architecture, and in this case it will be update slot status Python 3.12 and x86_64. After clicking the create button on the previous step, we can see that the Lambda function is successfully created. Now we will create the rules for IoT coding that will connect the IoT core to Lambda function. Now return to IoT core by searching it in the search bar, expand message routing and select rules on the side navigation bar. Then click on Create Rule button on the top right corner. Enter the rule name and add rule description if needed and click Next. Enter the desired SQL statement in the box provided and click Next. Now you should be able to see this page for rule action addition. In the drop box, search for Lambda and select it. Then in the Lambda function section, select the Lambda function that needed to be triggered when message received in the topic in the Lambda function session. After completing the last step, now review the information entered and click Create after confirming. And we will return to this page after clicking the Create button on the previous step, and we can see that the rule is successfully created and added to the list. Now return to the Lambda function created, and we can see that AWS IoT is added as a trigger for the Lambda function when message received in AWS IoT for a particular topic.
Hello, sir. For connector configurations, first of all, search for the connector from the search bar. Then, now you should be redirected to the connector page. Click on the Create User Pool button. It will bring you to the configure sign-up experience. Select types of provider and its options to sign in. Then, click Next. Next, it needs you to configure security requirements. Configure your desired settings such as password policies, multi-factor authentications, MFA methods, and user account recovery. After you've done all of that, click Next. It will continue with configuring sign-up experience. Set up service sign-up, attribute verifications, and user account configurations, and the required attributes. After complete, click Next. Next, it will bring you to configure message delivery. You have to select the email provider and set up the email address before clicking Next. Next, it will call you to integrate your apps. Enter a unique user pool name for the user pool. Next, continue to enter your domain prefix. After you've done that, it will call you to select the app client type and insert app client name for your connector client. Now, after you've done all of that, review the configuration before creating a user pool. After done reviewing, click on Create User Pool. You can update the hosted UI customization on the app integration section. Now, next, import the existing Amazon connector resource into the project. Go to Lambda console by choosing Lambda, then create the function. Create a function for it. Type the integrated code and deploy to Lambda. Then go back to connector, select the user pool that's created just now, and find the user pool property sections. Then click Add Lambda Trigger and add the Lambda Trigger that created just now. This Lambda Trigger will save user detail into DynamoDB's table.
For AWS Amplify, first choose Amplify hosting to host the web app. Then select the GitHub for AWS Amplify to get the source code from GitHub. Then install and authorize AWS Amplify in GitHub and check the only select repositories to authorize the selected repositories. Next, add the repository branch after the authorization was successful. Then check Allow AWS Amplify to automatically deploy all files hosted in your project root directory and input the app name, such as Smart Parking. Lastly, check if the detail is accurate. If accurate, click Save and Deploy to deploy the app on the AWS Amplify.
For the configuration of AWS DynamoDB, we first search Amplify and click on AWS Amplify. Then click on the app Smart Parking. Then click on Backend Environments and click on the Launch Studio. After that, in the sidebar located in the left side, click Data which is located under Setup. Then click on Add Model and enter the table name, attributes, and relationships that you want and repeat until all tables is added. After we finish added all the tables, click on the Save and Deploy and click on the Deploy to confirm the deployment. After that, wait for it to finish deploy and click on Done. As for the configuration of Amazon Event Bridge Scheduler, we first search Lambda and click on Lambda. Then click on the Lambda trigger Lambda for the Event Bridge Scheduler, which is Create Scheduler in this case. Then click on Configuration. After that, click on Permissions and then click on the link under the role name. After that, hover over Add Permissions and click on Create Inline Policy. Under Service, search Scheduler and click on Event Bridge Scheduler. Under Access Level in Right, select Create Schedule, then under Resource, select All. Click on Add More Permissions and then search IAM and click on IAM. Under Actions Allowed, search Pass Row and tick Pass Row, then select All under Resources. After that, click Next. Under Policy Name, enter its policy name, which is Create Scheduler Policy in this case, then click on Create Policy. In the sidebar, click on Roles, then click on Create Role. Select Custom Trust Policy and type servicescheduler.amazonaws.com in the curly brackets beside the principal. After that, click Next, then click Next again. Then under Role Name, enter its role name, which is Create Scheduler Assume Policy in this case. After that, click Create Role. Now search for the newly created role and click on it. Then hover over Add Permissions and click on Create Inline Policy. Under Service, search Lambda and click on Lambda. Under Access Level in Right, select the Invoke function. Then under Resources, select All and click Next. Under Role Name, enter its role name, which is Lambda Invoke from Event Bridge in this case. Then after that, click the Create Role. Copy the AIN in Create Scheduler Assume Policy in the clipboard. Then head back to Lambda page and click on the Invoke Lambda for the Event Bridge Scheduler, which is Update Reserve in this case. Copy the function AIN in Update Reserve in the clipboard. Then in Visual Studio Code, write down the parameters code in Create Scheduler Lambda and paste the AIN of Create Scheduler Assume Policy in AIN and the function AIN of Update Reserve in the role AIN. After that, change the directory to the root of the project and type amplify push to update the API. That's all. For the configuration of AWS Lambda, we first open Visual Studio Code and open the terminal of the root of the project and type amplify add API and select the following options: res, no, the name of your function, the name path, the AWS Lambda function name, and the runtime and any function template that you want to use. Then change the directory to the source of the newly created function and install node fetch by typing npm install node fetch alliance 2. After that, change the directory to the root of the project and type amplify push to deploy the new API into the cloud. That's all.